In this video, we're going to look at double integrals over general regions with rectangular coordinates. So the first thing we're going to do is start out defining what a rectangular region is in terms of polar, just like we did when we were looking at our section 5.1 when we first learned about double integrals over rectangular regions. So the way that we describe a rectangular region in polar coordinates is going to have some r value. This is our radius from A to B. And the angle of rotation is going to go from alpha to beta. So we start with Riemann sums, and here's the area that we are looking at. And then, of course, here is my rectangular region. Notice it has some delta r, and we have some rotation delta theta. Our area that we're going to be looking at is going to be 1/2 delta r, and then r of I minus 1, and that is looking at this point right here. And then multiplied by delta theta, plus r sub 1 delta theta, which is all of my rij's, delta theta. And as before in rectangular or Cartesian, we are looking at this area and this height. So of course the height will be a function of r. And we get our double Riemann sums. And those double Riemann sums we know then can be considered a double integration, where I have my function in terms of r and theta multiplied by r dr d theta, where my theta goes from alpha to beta and my r goes from A to B. Now, notice that when we go back to our dA, it is replaced by r dr d theta when we're working with polar coordinates, not just dy dx. It is r dr d theta. When the function is in terms of x and y, we can do our usual conversions, which is x is equal to r cosine theta, and y is equal to r sine theta, and dA is r dr d theta. Don't forget the r. So then if we look at our rectangular in terms of x and y over our area that we're looking at, we can rewrite it as our function in terms of r cosine theta and r sine theta. Don't forget the r dr d theta. Everything that we learned in terms of properties in section 5.1 over double integrals in regular, rectangular, or Cartesian regions still holds true for the polar rectangular regions. And of course, if we can do it in rectangular polar, then we can also do it in the general. With the general rectangular regions, we're going to have our alpha and beta still be going from, our theta going from alpha to beta. But now our r is going to be in terms of two functions, that is in terms of theta. In Cartesian or rectangular, we had type 1 and type 2 regions. In polar, we typically only have r is equal to some function of theta, rather than some theta is equal to some function of r. It's typically what we do. So we really only have this kind of general region, our region D. Which then brings us to if our function, which is in terms of r and theta, is a continuous function on a general region, polar region D, then our integration, our double integration over our region D becomes the theta from alpha to beta and our r from h1, a function h1 in terms of theta, and r is equal to h2 in terms of theta. F of r theta, don't forget the r, dr d theta. So express the region in D in polar coordinates and then evaluate the double integral over the region D. Now, if this was asking for just the area, then I probably wouldn't bother doing the integration. So the first thing is that I have some radius of 3, and then I also have some radius of 5. If they were asking me to find the area, this would be simply the larger circle area minus the smaller circle area. But they're asking me to describe the region and then, of course, to evaluate the double integral. So the region that I have, the region D, and this is actually rectangular, so I could use R. The region D is r comma theta, and since I have values for r in terms of numeric values, it's not a function of something else. This is a rectangular region, so I could use r. My radius is going to run between 3 and 5. My theta for one full rotation is going to run between 0 and 2 pi. So I'm asked to integrate from, and I usually do the theta first because my r is typically in terms of theta. So by default, I will go from 0 to 2 pi, and then I'm going to integrate the 3 to 5 of r, because all of these have this r, dr d theta. Then I'm going to do my usual integration, and so I'm going to have the integration from 0 to 2 pi. And I'm going to integrate this first, and I'm going to get r squared divided by 2, evaluated from 3 to 5, d theta. And as you know, I like to do this separately. And so I have 1/2, I'm going to have 5 squared minus 3 squared. This is going to give me 4 squared over 2, which is equal to 8. And so this is going to be equal from 0 to 2 pi of 8 d theta, which is just going to give me 8 theta, evaluated from 0 to 2 pi, which is just going to give me 16 pi units, whatever it is if we're talking about area, be units squared. Okay, and you could have totally done this without doing the integration. This one's another one that you can totally do without the integration. We have a circle centered at 0, 2 with a radius of 2. Using pi r squared, my answer is 4 pi. But we want to get used to taking something that is very familiar to us and turn it into polar so that we know what the answer is going to be, and it's just a process of getting more comfortable in polar. So a circle in general is going to be of the form x minus h, the quantity squared, y minus k, the quantity squared, is equal to r squared. So we're centered at the origin, so it'd be x squared plus y minus 2, the quantity squared is equal to 2 squared. X squared plus y squared minus 4y plus 4 is equal to 4. Y squared and x squared is equal to 4y. Now, r squared is equal to x squared plus y squared all day long. The y is equal to r sine theta all day long, and x is equal to r cosine theta all day long. So this gets replaced with r, and the y gets replaced with r sine theta. This should be r squared. So now where I am is r squared is equal to r sine theta. So r is equal to sine theta. Now when I build my region D, this is going to be r comma theta, and my r is going to go between 0 and r and sine theta. Then my theta, because we know that with these kind of circles, which are in polar form, these circles in polar form go from 0 to pi. So my theta is going to go from 0 to pi, not 2 pi, because of the equation in polar form. The equation of a circle in polar form goes from 0 to 2 pi. So now let's set up our integration. So my integration is going to go from 0 to pi, and then this will go from 0 to sine theta. And then I have r dr d theta. So this is going to be equal to from 0 to pi, and then it's going to be r squared evaluated from 0 to sine theta. Don't forget divide by 2. I already did the dr, just the d theta. So you know how I like to go do this to the side, and so it's going to be sine squared theta divided by 2 minus 0, so sine squared theta. So this is going to be 1/2 the integration of 0 to pi of sine squared theta d theta. And then I'm going to use the power reduction formula, so I know that the sine squared theta is equal to 1/2 minus 1/2 the cosine of 2 theta. And so this then becomes, I'm going to factor out a 1/2, so it's 1/4 the integration from 0 to pi of 1 minus cosine 2 theta d theta, and I'll let you all finish that integration. So what we did up above was starting to convert the polar from rectangular into polar. We're going to continue with this, and of course we're going to use the same rules, which is my x squared plus y squared is equal to r squared all day long. Y is equal to r sine theta, and x is equal to r cosine theta. So remember in pre-calc 2 where I'm like everything is x, y, r, please let go of the SOHCAHTOA. This is why, one of the many reasons why, not just because I'm a little cray-cray, it's because we really do need to get a better idea of what's going on. So the first thing is doing the replacement of x, which is equal to r cosine theta. And the square root of x squared plus y squared is going to be the square root of r squared. And so my x over the square root of x squared plus y squared is going to give me r cosine theta over r. So in other words, so we just have cosine theta. That's the easy bit. The next thing I have to do is figure out how I'm going to do the conversions on my limits of integration. So the easy bit is the conversions. Now let's go in the xy plane. This is y, so that these must be my limits for y. So y equals x, and y equals 0. So y equals x, and y equals 0 is the x-axis. This is x is equal to 3 and 2. So here's 2, here's 3. Now we can see if x equals y, then this is theta is equal to pi over 4. And since I started at 0, that means my limits of integration on the theta is from 0 to 4, or pi over 4. So we know what my theta, my region, so let's start building my region, because you know how I like to build that first before I jump into the integration. Since my theta is something I know right out of the gate, I'm going to just build that part of the theta. So that part is going to go from 0 to theta, which is less than pi over 4. Now, here's the interesting parts. So my x runs between 2 and 3. X gets replaced with r cosine. So 2 r cosine of theta is less than 3. We divide everything by cosine theta, and so we get 2 divided by the cosine of theta, less than or equal to r, which is less than or equal to 3 cosine theta. But we know that cosine is the reciprocal of secant, so it is 2 the secant of theta, which is less than or equal to r, which is less than or equal to 3 the secant of theta. So then, I don't know why I closed that. We now have two functions that contain r. R is going to run between 2 the secant of theta and less than or equal to r, which is less than or equal to 3 the secant of theta. Now let's go ahead and set up the integration. So my integration, which started from 2 to 3, 0 to x, I have x over the square root of x squared plus y squared dy dx is going to be equal to, from 0 to pi over 4, and from 2 secant theta to 3 secant theta. And then it'll be my numerator and denominator ends up just being the cosine of theta. Don't forget we multiply by r, and then dr d theta. So cosine theta, because I am integrating with respect to r first, is just going to be a constant. And in fact, I can think about squeezing that in between those two if I want. I can think of that as 0 to pi over 4. I can write my cosine of theta right here because it is a constant when I do this integration, to the secant of theta, 3 the secant of theta of r dr. Group that, d theta. So then this is going to be equal to, from 0 to pi over 4, I have the cosine of theta. Now I'm going to have r squared divided by 2 evaluated from 2 the secant of theta, and then 3 the secant of theta, d theta. I'm going to do this. So I'm going to have the cosine of theta multiplied by r squared, which is going to be 3. The secant of theta, let's pull that 2 out. The quantity squared minus 2, the secant of theta. I already squared that, look at that. Secant of theta, the quantity squared. So then this is going to be equal to cosine of theta divided by 2. And then it's going to be 9 secant squared theta minus 4 secant squared theta. So this is going to be equal to the cosine of theta divided by 2 multiplied by 9 divided by the cosine squared of theta plus cosine of theta, that should be a minus, cosine of theta divided by 2 multiplied by 4, and then the cosine squared of theta, which then just becomes, I have 9 over 2. Cosine over cosine squared is just cosine, which then becomes the secant of theta. And then minus, and this becomes 2, and the same thing, the secant of theta. And I think I'm going to leave it as 4, actually. I'm going to leave this as 4 over 2, so I can just add and subtract these. 4 over 2 secant. And I can just add these, and so I get 5/2 the secant of theta. Okay, now all of that was just so that I can make it an easier I'm going to pull out that 5/2 integrated from 0 to pi over 4. And then I have the secant of theta d theta. And we know that when we integrate the secant, we typically will use some sort of trig equation because the secant by itself is near impossible to integrate by itself, but we know we can multiply the numerator and denominator by the same thing. So just as a fresh reminder of Calculus 2, I have the secant of theta. If I multiply and I write it over 1, if I multiply it by the tangent of theta plus the secant of theta divided by the tangent of theta plus the secant of theta is going to give me the secant theta tangent theta plus the secant squared of theta. And then in the denominator I have the tangent of theta plus the secant of theta. And then I know that this is the derivative of that, and this is the derivative of that. So that means I must have had a 1 over u type of situation times u prime type of situation, which means that I have 5/2 the natural log of the absolute value of the tangent theta plus the secant theta evaluated from 0 to pi over 4. And I'll let you all finish that off. So it's just a nice little refresher of some pre-calculus 2 and some calc 2. So there's that one. A lot of work for that one. Now, personally, by the way, as I look at this, if I was asked to do this integration, I probably would not have chose to go into polar, because if I do this integration with respect to y first, x over x squared plus y squared dy dx, I probably would have switched the limits of integration from 0 to x and evaluated with respect to x first because, and this is the square root, because it looks to me more like a right out of the gate, a u substitution with the limit switched. And what I mean by this is that if I said let u equal the x squared plus y squared, then du with respect to x would have been 2x dx. And I see this x here, so I probably would have switched the limits of integration by switching the order and done a u substitution. However, that is not what they asked me to do, so I went through all of this to do what they asked me to do. Now let's take a look at this one. This is one in which we're kind of stuck doing the switching out in terms of the trig polar because it's 1 over x squared plus y squared. I mean, you can totally do it without probably, but I think it's going to be more of a hassle. So the first thing I'm going to do is do the switching out of this part, right? So again, I have x is equal to r sine theta, or r cosine theta, r cosine theta, y is equal to r sine theta, and r squared is equal to x squared plus y squared all day long. Easy peasy lemon squeezy part is this replacement. This 1 over x squared plus y squared, the square root, is 1 over the square root of r squared, which is 1 over r. Easy peasy lemon squeezy. Now, let's take a look at the limits. So my x is going to go between 0 and 1. So 0 and 1 for x, because this is x equals 0 and x equals 1. My y is going to be stuck between x and y squared, or x between y equals x and y equals x squared. So here is the line y equals x, and then here is the x squared part. So it's something like that. So this is the region I'm looking at. Now my theta, as before, is pretty straightforward. It's going to rotate between 0 and pi over 4. So as I start building my equations here, I'm going to have before I start doing my integration replacements, I like to build my region. So d is equal to r comma theta. Now theta is the easy part. We know it's going to run between 0 and pi over 4. The more interesting part is what happens when with the r part. So let's take a look at my picture here. This is where r is going to run. So this is my r. And this is also my r, and this is also my r. So you can see that r, by my picture, starts at 0. So the part we have to be worried about then is if r runs between 0 and the thing that's going to constrain my r is the x squared part. That's the part that's really going to constrain my r. So how do we do that conversion? Well, let's say y is equal to x squared. That means r sine theta is equal to r squared cosine squared theta, which means that if I divide everything by r and cosine squared, I'm going to have sine theta divided by cosine squared theta is equal to r, but that's kind of ugly. So r is going to be between tangent theta and then secant theta. So r is going to run between 0 and tangent theta secant theta. So r tangent theta secant theta. Okay, so now let's do our integration. So this integration is going to run between first my 0 to pi over 4 and 0 tangent theta secant theta. And then my integration, remember, was 1 over r. It's that 1 over the square root of x squared plus y squared is 1 over r. Multiplied by r, dr d theta. And you can see that my r's cancel. So that's really kind of nice. So this is going to be equal to from 0 to pi over 4. And then I have 0 to tangent theta, secant theta, dr d theta. So this ends up becoming from 0 to pi over 4. And this is 1, so I end up with just r evaluated from 0 to tangent theta, secant theta, d theta. And this one's easy. I don't have to go off and do it off to one side. So this is equal to the integration from 0 to pi over 4 of tangent theta, secant theta, d theta, which becomes the integration. This is a nice, easy integration. This just integrates into the negative, or this integrates into the secant of theta. So this is equal to the secant of theta, evaluated from 0 to pi over 4. And I'll let you all finish that integration. Now, if I compare A to B, right, the hardest thing about B was finding the correct R values. The actual integration, once I got everything in the right places, easy peasy lemon squeezy. This one, it wasn't too bad to find my limits because I went from 0 to y instead of x. I went from 0 to x is equal to y. The hard part about this one was the actual integration. This is not an integration I would have done with polar. This one, once I got my integration limits correct, polar was easy peasy lemon squeezy. So this is just one of many techniques. On the final exam, if I give you that, you integrate however you want. I personally, if I gave you A, I'd probably change the order of integration and change the limits of integration and just do a regular integration. B, I would probably find my equivalent polar, and because it was an easier integration. Now let's take a look at this one. So the first thing I like to do is do the replacements. And by this point, we're like, we got this. This ends up becoming r squared squared. We know that one's the easy bit. I'm going to draw my picture. My x is going to go between 0, because remember, oh, got to pay attention to this. This is y equals, and this is y equals. Look at that. This is x equals, and this is x equals. So I'm going to start from 0 to 2. And then if I take a look at this, and we should get a little familiar with this, when I have x is equal to plus and minus the square root of 4 minus y squared, then I must have had x squared is equal to the square root of 4 minus y squared, which means that this is what I have, is a circle with a radius of 2. Now, this is not finding the area, so I'm not going to do an easy peasy lemon squeezy. But I also know what my r is. My r is going to run between 0 and 2, and I also know what my theta is. So my region of f of r theta, this one's actually not too bad to do this region. Theta is going to run between 0 and pi, because I only have half a circle. And my r is going to run between 0 and 2. So my integration from 0 to pi, from 0 to 2, of r squared squared multiplied by r dr d theta. So this is going to be from 0 to pi, from 0 to 2, of r to the 5th, and that's because I have r squared squared multiplied by another r. And then I don't know why I didn't have a d theta there. Let me go ahead and put my d theta. Have the theta, don't have the d theta. So d theta. And then dr d theta. Nice easy peasy lemon squeezy from 0 to pi. We have r to the 6th divided by 6 evaluated from 0 to 2. D theta. And we know this part is going to be 2 to the 6th divided by 6. So then this is going to be equal from 0 to pi. And 2 to the 6th, I believe, is 64, I think. let me check, 2 to the 6th is 64. 64 divided by 6 and d theta, which gives me the 64 over 6, which is 32 divided by 3, evaluated from 0 to pi. So 32 divided by 3 pi. And there is my final answer, which actually wasn't too bad. Okay, now we're going to talk about areas. Areas between two polar curves can be found by doing the alpha to beta, my r between my first function and my second function, so between my top function and my bottom function, and I use that word loosely, and then we have 1r dr d theta. So find the region bounded by, they're asking for the area of the region bounded by the polar axes and the upper half of cardioid. So first of all, let's do a quick little sketch. So this is the polar axes, and then this is my cardioid, very poorly drawn. And what they want is this region right here. That's the region we want. Now we know that my region D is, I always like to start out with that, so f of r comma theta. My theta is pretty easy. It goes from 0 to pi. Less than theta, which is less than or equal to pi. My r starts at 0 and is constrained by this function. So my r is going to go between 0 and that function 1 plus cosine theta. When I do my integration, I'm going to integrate from 0 to pi, from 0 to 1 plus the cosine of theta, of 1r, don't forget the r, dr d theta, and you go from there. I'm going to let you finish that. I'm just going to set up the integration there. Let you all finish the integration. It's not bad. I have to do a little bit of a power reduction formula on the cosine squared, but you got that. This one, the region D, the petal of the first quadrant of a fourth leaf rose. So it looks something like this. Okay, so this is my polar axes. Now I'm in the first quadrant for this, so that tells me that my theta is going to run between 0 and 2 pi. So I'm in this first quadrant. So my region D is f of r theta, such that my theta is going to run between 0 and pi over 2. So theta and pi over 2. My r is going to be constrained between 0 and this function. So my r is going to go between r and this function, which is the sine of 2 theta. Once again, I'm going to set up my integration. So I integrate from 0 to pi over 2, from 0 to the sine of 2 theta, of 1r dr d theta. And of course, I'm going to let you go ahead and finish this one. Let's take a look at the next example. We have the region D, which is inside the x squared plus y squared is less than or equal to 4, and to the right of the line, x is equal to 1. And as before, you know, I love to draw the picture so I can figure out what my region is. So I'm going to draw my picture, which is a circle centered at the origin with a radius of 2. And then, so it's going to be within this circle. And then I want it to be to the right of this line, x is equal to 1. So this is the region that I'm looking at. So for this one, what we're going to want to do is we're going to find our theta, and we need to figure out where this thing crosses so we can figure out our theta, what our theta is. So what we have is we have an x value, which is 1. So we have 1 squared plus y squared is equal to 4. So we have y squared is going to be equal to 3, so y is going to be the square root of 3. Then I know that my r happens to be 2 because that's this part. Now I know that the sine of theta is going to be my y value over my r value. It's a square root of 3 over 2, so we know that that happens when theta in quadrant number 1 happens to be pi over 3. So I know what my theta runs between. So doing my region, f comma r theta. My theta is going to run between 0, theta, and pi over 3. Now I just have to figure out what's happening with r. Now we know that the largest r is going to become is 2. So we know that the upper part of r is 2. What we have to do is figure out this lower part. And we have x is equal to 1. That's the lower part. But we know that x is equal to r cosine theta, which is equal to 1, which means r is equal to 1 over the cosine of theta, which gives me the secant of theta. So that's where this starts, is at the secant of theta, and then it goes up to 2. So this is the secant of theta, which is less than r, which is less than 2. And now I'm ready to do my integration. My integration is going to be from 0 to pi over 3, from secant of theta to 2, and then it's r dr d theta, and of course I'll let you finish off that integration. The next thing we get is the volume, so this is going to be the more interesting stuff. So our volume is going to be our regular region from, or if it's a rectangular, if it's a non-rectangular, if it's a general region, it's region D. F of r theta, r dr d theta. And so, of course, we go from theta is equal to alpha to beta. R is equal to a to b if we're rectangular. If it's general, then it's going to be theta is from alpha to beta, and r is from my first function to my second function. And then using that information, let's find the volume of the solids given by this. So the first one is we're in the first octant, which means I am constrained between x is equal to 0, the plane x is equal to 0, the plane y is equal to 0, and the plane z is equal to 0. And the paraboloid z is equal to 1 minus x squared minus y squared. So clearly I'm not terribly good at drawing the picture, so what I'll do is let's just jump right into what I'm looking for. In rectangular, I'm looking for the volume, which is the double integration d over z dA. So I have the z part, which is, of course, 1 minus the 4x squared minus 4y squared. So let's go ahead and do that conversion. So I've got z, which is equal to 1 minus 4x squared minus 4y squared. This is going to be equal to 1 minus 4x squared plus y squared, which we know is r squared all day long. So we have 1 minus 4r squared. So now we got a replacement for this. And then now all I have to do is think about where I am in the first octant. So if I draw a quick little picture of the first octant, I have 1 minus 4x squared y squared, 1 minus, so if I think about the trace in the xy plane, so I can think about this as just the xy plane in the first octant, we have this circle. So when z is equal to 0, so I'm going to do the trace. When z is equal to 0, I've got 1 is equal to 4x squared plus 4y squared. And that means I have 1 is equal to 1 over 4, and that's x squared, and then y squared, and then that's 1 over 1 over 1 over 4, 1 over 1 over 4, which is, of course, the circle centered at the origin, whose radius is the square root of 1/4, which is 1/2. So this is 0.5, this is 0.5. This is the region that I want, because I'm in the first octant. So I know in this region, my theta is going to run between 0 and pi over 2. So let's describe the region. Try this again. Let's describe the region. D f of r theta. I'm going to run between 0 and pi over 2. And then my r, you can see, is going to run between 0 and the most it's ever going to be is 0.5. So this is actually a rectangular region, so it's going to run between 0, r, and 1/2. So then I now have my bounds. I'm going to run between 0 and pi over 2. I'm going to run between 0 and 1/2. My z is going to be 1 minus r squared. Don't forget the 4. R dr d theta. And of course, I will let you finish off that integration, so the integration isn't too bad. Now I want to know the solid inside the cone and below the plane z is equal to 1. What they're telling me what I want to do is find, as a hint, find the volume of the solid bounded by the cylinder between the planes z equals 0 and z equals 1. Now, I am inclined not to do the integration, right? Because I know the volume of a cylinder is going to be the pi r squared h. To save myself some time, I know that r happens to be 1 because they're telling me to use this as a hint. And they're also telling me my height is 1 because I'm going from 0 to 1. So to save myself some time, of course I can do it by integration, totally do it by integration, is just going to be pi, and that's it. And it's going to be units cubed, whatever the units are, because we're talking about volume, just to save myself some time. Now what I want is the volume of the solid above the disk that I just built, but below the cone. So we know that the cone, z squared, is equal to x squared plus y squared. That means z is equal to, normally plus and minus, but I'm looking for a specific region, so I'm only taking the positive part, of x squared plus y squared. So then the volume that I'm looking at is the volume over my region D of my x squared plus y squared dA. Now, for this, I know that x squared plus y squared is equal to r squared all day long. So that's that part. So I know that's the square root of r, so it's just going to be r. And then don't forget I need to do r dr d theta. That's that part. Now, I am going to be looking at a cone, and that means I'm going to go from 0 to 2 pi. So from 0 to 2 pi. My r value, they're telling me that I want to be below z is equal to 1, so I know my r value is going to go from 0 to 1. So what I have then is the integration from 0 to 2 pi, from 0 to 1, of r squared dr d theta. This one I will actually finish through, and so I'm going to have from 0 to 2 pi of r cubed divided by 3 from 0 to 1 of d theta. Squeeze in that d theta. And my d theta, I don't know why I keep dropping that, it should be dr d theta. So this is going to give me just 1/3 integration from 0 to 2 pi of d theta. So I end up with this as just being 2 pi divided by 3 units cubed. The region I want, though, is going to be this region that I just found, subtracted from my first disk. So the disk I found before was the volume of pi minus 2/3 pi. My final answer is 1/3 pi units cubed. So that's my final answer, units cubed. Okay, now this one I've got this really cool little picture. In this really cool little picture, we want to find a solid that lies under the paraboloid, but inside the cylinder. So we're really looking at this region down here, and it's a solid. So the way that we're going to approach this is that we're going to first do the replacements. So I'm going to look at my cylinder, which is on the trace on the xy plane. So the trace on the xy plane, z is equal to 0. That this is going to be x squared plus y squared is equal to x. And so this is r squared is equal to r cosine theta. So r is equal to cosine theta. That tells me that I have a circle centered at the point, well, 1/2. So it'd be 1/2 out. So my center for this one would be, for this circle, which is the cylinder, is going to be on the x-axis. So it would be 1/2 right here. So this is what it would look like on the x-axis. This tells me that my theta is normally going to run between 0 and from 0 to pi. But in this case, I'm going to run from pi halves, negative pi halves to pi halves. So my theta is going to run between 0, from negative pi halves and pi halves. So negative pi halves to pi halves. That's my theta. So my region D, f of x of r comma theta, r comma theta, r comma theta. So that takes care of the theta. And my r is going to be constrained between 0 and that function. So it's going to be 0 and r and that function, which is the cosine of theta. Now, the function I'm looking at is this. So that is going to be the height at any given time. So we know this is going to be from 0. Why do I want to do 0? Because I'm used to 0. So I have from negative pi halves to pi halves, from 0 to the cosine of theta. And this is just r squared. So this is my function, so r squared. And then it's going to be r dr d theta. And so I end up with from negative pi halves to pi halves. And then I have r to the third, so r to the fourth actually, because it's r to the third. So r to the fourth divided by 4, evaluated from 0 to the cosine of theta, d theta. So this will be equal to from negative pi halves to pi halves. Bring the 1/4 outside, the cosine to the fourth of theta, d theta. And I'm going to use the power reduction formula. So I'm going to write the cosine to the fourth of theta as equaling 1 is cosine squared squared. So the cosine is squared theta, the quantity is squared. And then I'm going to use the power reduction formulas from there so I can make my integrations pretty straightforward. Okay, so last thing, this is it for the quarter even, and for this section, is looking at improper integrals. So as before, we can do improper integrals with our polar. The point that we want to really focus in on is if we want the entire plane, then my theta is going to go between 0 and 2 pi, and my r is going to go from 0 to infinity. This gives me the entire plane. So then my 0 to 2 pi and r to infinity can be rewrote by doing the limit as a approaches infinity, and then change my limit from r equals 0 to r equals a. So let's go ahead and take a look at this example. They're asking us to take the double integral from negative infinity to infinity and negative infinity to infinity of e raised to the negative x squared plus y squared over 2 dy dx. It can be defined as a disk d sub a of radii a centered at the origin. And as a increases without bound, we end up with taking this god-awful and turn it into something like this. We want to show that this god-awful integration becomes just 2 pi. Now, there is a typo here. This should be, I believe this should be this, like this, and like this, and like this. So the first thing is that. So, doing our regular replacements, this is going to be, not this part, this is going to go from 0 to pi, 2 pi, because that's this replacement. Remember, we're looking at R2, and my theta is bound between 0 and 2 pi, so that's that replacement. And then we have from 0 to pi, or 0 to infinity, and because we know our r is bound between 0 and infinity, we have e replaced with a negative. X squared plus y squared is equal to r squared all day long divided by 2. And then it's going to be r dr d theta. So then we're going to do, this is going to be equal to, from 0 to 2 pi of the limit as a approaches infinity from 0 to a of e raised to the negative r divided by 2 r dr d theta. And this is actually not too bad of an integration because I have the r dr. So I know if I have e raised to the negative r squared over 2, that d dr theta would have been negative e raised to the r squared, negative r squared divided by 2, which gives me just also 2r divided by 2, which gives me just r. So I'm missing a negative, so I'll make that adjustment when I do the integration part. So then this is just going to be equal to, from 0 to 2 pi of the limit as a approaches infinity of e, negative e raised to the negative r squared over a, r squared over 2, excuse me, r squared over 2 evaluated from 0 to a d theta, which is going to be equal from 0 to 2 pi, the limit as a goes to infinity of negative e raised to the negative r squared divided by 2 minus the limit as a goes to infinity of negative e negative r squared divided by 2, where I'm going to have my r squared, it gets replaced with a. So let me replace this with a. That gets replaced with a. And this r squared over here gets replaced with 0. D theta. Now here's the thing. This is the same thing as negative e 1 over e raised to the a divided by 2. And we know as a gets really large, this term goes to 0, so this term will go to 0. So this is just from 0 to 2 pi. Now, because of the fact that this is a negative, it becomes plus, and e to the 0 is 0, is e to the 0 divided by 2 is e to the 0 all day long, which is just going to be 1. So this is going to be a minus minus, so it becomes plus 1 d theta. Doing a regular integration, we get 2 pi. And there we have proved it, and we are done.